All right, folks, moving on. So now, instead of just trying to conceptually understand what's happening with this side-side angle pattern, we're going to actually look into some problems algebraically. Now, each of the three examples that we're going to do are actually going to be the same three pictures that we analyzed in the very beginning, where we drew them to scale. You will not generally be drawing anything to scale, so we need to understand these from a true algebraic perspective. So, for example, on this first one, what you can see that I've already done is I took my information for my triangle, just drew in any old triangle. Doesn't even matter that this doesn't look like 13.5 versus 5.6 or necessarily 62 degrees. Doesn't make a difference, because what we know is that if this were drawn to scale, our picture would actually look like this one. But that's okay. So the thing that I do want to point out is because we already know that this triangle is not going to exist from that previous page, I did not bother drawing the potential second triangle. In reality, you would need to draw the potential second triangle because you don't know what's going to happen. You don't know if it's going to be a 0, a 1, or a 2. So let's take this, knowing where we're going to land, and let's find out what happens algebraically. So how would we know this? So the first thing we would do is we would look at this and we'd say, oh, I can see that connection, that link between the side and the angle across from it. So that would tell us that we could set up a law of sines question. So we would say our 5.6 over our sine 62, and we only have one choice of an angle to find, so we would say 13.5 divided by the sine of b. We're solving for an angle this time, so that's definitely going to change some things for us. So if I cross multiply this, I would end up with sine b, and in my numerator I would have my 13.5 times my sine 62 all over my 5.6. Okay. Now, there are several places where it's going to warn us this is not going to work. So if we type all of this into our calculator, what we're going to get is sine b equals 2.13. Okay, so if you type all that in, that's what you're going to get. Now, right now, this should be your first caution that you're saying, whoa, whoa, whoa. We know that 2.3 is not possible for a sine triangle, for a triangle with sine, because there's no way that the opposite over the hypotenuse would give us something that's more than 1. We can think graphically. Now, let's say we don't catch the warning right here. If we try to type this in our calculator, let's say because we're looking for an angle in our calculator, then we could type in that b is equal to the inverse sine of 2.13. If we try to type that in, inverse sine 2.13, sure enough, you get a domain or an error message, okay? So because we get this error, where it says not possible, various ways it might yell at you, our conclusion is no triangle. And that's all that you would need to do. You would just show that mathematically you get something that's not possible, and then you would write your conclusion. So, moving on. Our next problem is the second picture from the previous page. So we know that if it were drawn to scale, it would look like this. You'll notice that when I drew mine definitely does not look like it's to scale. This does not look like a 103-degree angle, but that's no big deal. I am going to use multiple colors here to make this process a little bit easier and clearer for us to follow. So the first thing that I'm going to do is I'm going to think about this little link, okay? And I can set up my law of sines. I can say 22 over my sine 103 is going to equal my 14 over my sine c. So just rearranging again, I'm going to say sine c, and thinking my cross multiplying for sine 103 divided by 22. So when I type this in my calculator here, I'm going to get my 14 and my sine 103. I'm going to divide that by 22. Now I have a nice number that's less than 1, so I'm happy. Then I'm going to do inverse sine of that because I'm looking for the angle. So I'm going to recall that answer. And sure enough, I get that angle C is 38 degrees. So I'm happy with that. So what I'm going to do is I'm going to do a couple things. I'm going to take that 38 degrees and I'm going to come put it up here in my picture. And I'm specifically going to put it in in a different color. So I've got my 38 degrees here. Then I know that this 38 degrees is actually going to be the same as this angle right here. Because remember, it created an isosceles triangle. So if this side really did swing in, it would create a 38 degrees right here. This angle is the same as this angle right here. Now, because of that, I can fill in every other angle. If this is 103 and this is 38, then this angle right here has to be 39 degrees. If we want, we could even write that out, that our angle B is going to be our 180 minus our 38 minus the given of 103. Okay, no big deal. Notice our triangle is almost isosceles. On this triangle, I have my 38. I complete my supplement and I get 142. And immediately I say, whoa, there is no way that this is possible. This triangle cannot exist. Immediately, because the angles are greater than 180 degrees. So we can just stop. This one's done. I can just ignore that for the rest of the problem and I continue on back over here. When I come back to this triangle, I do still have one more piece to find. I need to find this segment right here. I'm going to use the original link of 22 over sine 103. This should look like the first day's homework, equals side B over the sine of my 39. Now remember, these angles are about the same, which means these sides should turn out to be about the same. So sure enough, when I complete that algebra, I get that side B is 14.2. And I'm all done. I can put that in my picture if I want. And I'm all done. We have one more example to do, and that's what we do when we actually have two triangles.